Test, test. Can you hear me?
Hello, can you hear me? I can hear you.
Okay, very good. Okay. Uh, let's start today.
Okay, thank you.
Yeah. Um, First, I wish to review the material that we have discussed so far, and after that, we are going to move into uh, today topics. So um, let me share some slide. Okay. Yeah. So let me review a few things here. At the beginning, I think you remember that we discussed about the vehicle forward dynamics, and it was a very simple things. We applied equilibrium equations, and we derive equations to compute the acceleration of the vehicle, and mostly we focus on the level road and also on the inclined road. So at the end of this chapter, you have some formula that you can use to calculate the force, whether it is normal or it is in the longitudinal directions, and you are able to compute the acceleration for a given force. So those are the main issue, and then we changed our discussions to the tire dynamics, and here you focus only on the tire only, and we discuss of the tire coordinate system and also two angle, which is one of them is the chamber angle, and we also discuss about rolling resistance. The rolling resistance is the force opposite to the movement. So if a tire moving forward, then the rolling resistance force moving backward, and the rolling resistance make the tire stop rolling, and this happen due to of elasticity of the tire material. Okay, so and we focus also on a set of force that happen due to the angles of the tire, right? And the alpha and gamma. So alpha is the if the steering angle, and the gamma is the sort of the chamber angle. And the chamber angle may happen if you are making turn, right? When you turn your vehicle, you produce a two angle, that is the alpha angle and also gamma angle, and due to the alpha angle and gamma angle, then you produce a tire force in the lateral direction mostly. So that was the subject of discussion in this chapter, where the tire dynamics. So we discussed practically the Fy of the lateral force due to the movement of the vehicle. That was chapter 3. Chapter 4, talking about the drive line dynamics. We focus on the rotation of the engine and also the torque of the engine. We already has understanding about this distribution of the torque as a functions of engine rotations, and we understand that there is an optimum frequency rotation of the engines, omega 1 and omega 2. And we wish to operate the engines within this optimum frequency. And the optimum frequency allow us to use the engines at the optimum efficiency, and that optimum efficiency may be 0.27 or 0.3 efficiency ratio. And from that, we set up the omega 1 and omega 2, which is the optimum frequency. And the main equation we understand in this driveline dynamics is two equations. One relate the torque of the engine to the force on the wheel, Fx, from the Te, torque of the engine, to Fx, the force on the vehicle. And the second equation is about rotation of the engine and the velocity of a car. So we have two equation only. We only have a two equation. That is the relationship between engine and the car, force and velocity. And we also have some equation that we can use to design the gear ratio, right? So at the end of a driveline dynamic, then you can design the gear to reach the velocity you wish to, and you understand the relationship between engine and also the force, right? However, the actual force Fx that acting on your car is not only the functions of the power of the engine, but also the frictions, which we discussed in the tire dynamic. So the Fx will be determined by the frictions and also by the power of the engine. And after that, we discuss about the steering dynamic. In the steering dynamic, we wish to understand the kinematics of steering. Of course, we try to design a kinematic system such that a vehicle can move without in the smooth fashions, without slipping at any of the tire. And a kinematic system that allow us to produce these Ackermann conditions is a 4-bar kinematic system. And we also understand the effect of beta, which is the angle of one of the bar, and how it affects the movements of the vehicle. Also in this chapter, you compute the radius of rotation of a car, the maximum radius and the minimum radius, so you know the space required for a vehicle to move around. And that is what we discuss in the steering dynamic. And at the end of this chapter, we discuss about the movement of a trailer following a truck. And in that section, we discuss two conditions of the relative position between trailer and the truck: jackknife condition and unjackknife conditions. Jackknife conditions may happen if the truck at a high speed suddenly apply brake, and the trailer may move in the uncontrolled fashion. At the section, we also have a simple differential equation that controls the movement of the trailer following a truck. So if we know the kinematic movement of the truck, then we can compute how the trailer will follow the truck by solving that differential equations, right? So we now understand how the trailer may follow behind behind the truck. And so today we discuss chapter 8 about suspensions. Yeah, suspension is a simple structures that we use to support the body of a car. So suspension is a structure that connecting the wheel to the body of the vehicle. And we must understand what is the purpose of a suspension. What is the optimum design of the suspension? That will be the subject of discussions today. So let me get back to the slide. I already prepared some slide for this session. So I think we can use the slide. Okay, so today is a chapter 8 about the suspension mechanisms, and we will start from a traditional suspension system to a more advanced suspension system such as mid-curve that allow us to have an independent suspension between left and right. And so let's see about this suspension design. Okay, we start with a traditional suspensions, which is a solid axle connecting left and right, and there is no independent movement between left and right of the tire. And then we discuss about the independent suspensions, and we discuss about the roll center, how the body of a car will rotate when the suspension move, right? And a number of criteria of design of the suspension is a TOE, the caster angle, the chamber angle, and the thrust angle. So all of those things will be discussed. We also will discuss the kinematic movements of the car body. When the suspensions develop certain angle, for example, chamber angle, for certain degree, then how much the car body will move up and move down. Okay. I think I'm going to skip the theory of the caster theory, but I will provide you a summary. So all of those things are the things that we will cover today. We start with the function of the suspension. So suspension essentially is an engineering structure that is designed to connect the wheel to the vehicle body. And it has a certain important aspect here. So it's allowed the relative motions between the wheel and the vehicle body. So the wheel can move independently, and this sort of independent of the vehicle body. So we expect the wheel can move independently, and the suspension should not move in just a second. Yeah, so we expect there is no forward and lateral movements of the vehicle body. So what we allow is only sort of the vertical movement. Okay, so that is a criteria that we wish to achieve. So the suspension need to has a rigidity in terms of forward movement and lateral movement. The only movement that suspension should allow is only in this in the vertical axis or z-axis. And however, as the vehicle should be able to be controlled in the steering, so the suspension should allow the steering, and 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 most importantly is suspension should be able to suppress vibrations. Okay, so this kind of performance that we expect from suspension, that suspension should suppress vibrations. Suspension is a structure that connect the wheel to the vehicle body. Suspension should not allow the forward movement and the lateral movement. So the only movement that suspension is allowed is vertical. Suspension should allow vertical motions of the vehicle body, suppress vibration, and allow steering, right? So those are the functions that we wish a suspension system to have. And engineers have solved this problem. What kind of structures that you can make to allow this requirement to be fulfilled? And we start with a traditional suspension system, which is a solid axle. So this is your tire. This is your tire, and the simple suspension is just a solid bar here, connected by this leaf. So this is a very simple suspensions. So only the bar and the solid leaf, and the vehicle body. This is the vehicle body, right? And the vehicle body is connected at these two ends. Okay, so the suspension system, it is the axle here and the leaf. So as you can see, this is a very simple structures. We have a simple structures connecting the body of the vehicle to the tire. And that suspension structure is only a leaf and an axle rod, right? So it's a very simple, suspension structures. And we still use this kind of system until now, particularly in some car. Not all the car use this system, and particularly for the rear of the wheel, right? For the front of the wheel, we use a different system, different suspension, but for modern car, we still use these simple structures. It has some weaknesses, clearly, but before we discuss the weaknesses, we has to introduce a quantity called a mass ratio. Mass ratio is essentially MS, which means the mass of the supported system, and MU is the we call it unsprung mass. But what we mean by this unsprung mass is the mass of the wheel and the axle and the brake system. Okay, so we differentiate two masses here. The first masses is the one that's supported by the suspension system, and the other that attached to that suspension system, or we call it unsprung mass. So epsilon is the ratio between, you can imagine this is as the car body, and this is the structure that support the car body. Including of this is the wheel, the brake, and the axle. So this is the car body divided by the supporting system. And we define this as a mass ratio. Generally speaking, if the ratio is high, which is mean the unsprung mass is low and the car is heavy, but the supporting system is light, then we improve the comfort or the riding, right? And we can improve the comfort level. But the vehicle may be rather difficult to control or stability is hard. Okay, so if the unsprung mass is heavy, then the stability is better in terms of the driving stability, right? Okay, so this particular suspension system, we call it Hotkeys suspensions, Hotkeys suspension. And because this Hotkeys suspension is extremely simple, so it has a very quite a big MU here, because you have a single axle. As you can see that this single axle is rather heavy, although it's simple. And the leaf spring also rather heavy. So you can assume that this suspension system is quite heavy. So generally speaking, it has a low mass ratio, right? So which means it's work quite well in absorbing a bump, but it also has a very good stability in driving, right? And now, what is the problem associated with this kind of a suspension system or a Hotkeys suspensions? One of the problem is instability of the suspension system. If you accelerate and you may have some movement, however, if you and the leaf spring deform in this fashion, like a S-shaped letter. So this S-shaped form of the leaf spring. However, when you take a break, and it's take this shape, right? So clearly we are not happy with this, because that will be a lateral, not a lateral, a longitudinal movement of the suspension system. At the beginning, I mentioned that the one of the best suspension should only allow the movement in vertical direction, but not much movement in the forward directions. So that is the definition of a good suspension. So good suspension only allow movement in vertical, but do not allow movement in the forward direction. And clearly that this phenomena is hard to control, right? So the tire not only move in the vertical direction, but also move in the horizontal direction due to this S-shaped deformations, right? Okay, so that is a difficult issue. Clearly that the leaf spring may twist, may bend. Yeah. Okay, so it's produce what we call as a caster, negative caster. So if the spring is long, clearly the stiffness will low, the comfort level is improved, not the stiffness is not so high, the stiffness low, vibrations, it's provide a better ride, but it's easily bend and easily twist. So you're going to feel the movement in the forward direction, right? So that is the limitations of Hotkeys suspensions. And engineers come up with a simple idea called an anti-tramp instrument. An anti-tramp instrument, it is shown in here, right? So what we did is we add a simple structure here, and also by pin joint. And with this simple additional structure, we can prevent the S-shaped deformations that happen along this leaf spring, right? So a simple anti-tramp structure can be added, and this anti-tramp prevent the longitudinal movement. So we can prevent the movement in these longitudinal directions, and improve the stability of the suspension. With this setting, now the suspension will only move in vertical direction, which is achieve the purpose that what we wish. So the anti-thrump may stop the S-shape deformation, but the twisting still may happen, right? So a small improvement in the performance of the suspensions. Okay, that is the earlier problem of this Hopkins suspension system, and a simple solution by introducing the anti-thrump mechanisms. But the other problem with the leaf spring is it can't be introduced at the driving wheel, because the driving wheel has to be able to be steerable. So you should be able to steer the wheel, and the leaf spring prevent you from having the steering mechanism. You can't have a steering mechanism with leaf spring, right? So as a result, you can't attach a driving mechanisms, right? So clearly that this particular suspension is only applicable if you put it at the rear of the vehicle, not at the front of the vehicle, where steering mechanisms is necessary. That is sort of the limitation. In the previous slide, I said that a good suspension should not allow a movement in the lateral direction, in the direction of the vehicle lateral. So the vehicle should not move in the front relative to the wheel, right? Relative to the tire, but also should not move in the lateral direction. So now, if we use an anti-thrump mechanism, then we can prevent movement in longitudinal direction, right? So the longitudinal direction can be stopped. However, we cannot stop the movement in lateral direction of the vehicle. So we need additional structures that block or stop the lateral movement of the vehicle. And this can be achieved by introducing sort of this kind of a linkage, right? So the linkage have some stiffness in this lateral direction. So now we can stop the curve lateral movement. Okay, so with this particular structures. And so now, by introducing two systems, the first system is this anti-thrump to prevent the movement in forward directions, and a simple triangulated linkage, and that prevents the lateral movement. So by introducing these two mechanisms to the suspension system, we can reduce the forward movement or the longitudinal movement, and also the lateral movement. So the only movement that allowed by this suspension is a vertical movement. Okay, so this is one of the solutions. The other is more advanced solutions. In this case, you have practically the same with previous one, but you have these structures, and this pen arm. This is called pen hard arm, and this will prevent the movement in the lateral direction. So similar to this triangle, right? So the purpose is to sort of prevent the movement in lateral directions. Now, Now we introduce these more complex structures, and this is a 3-bar linkage, and this will be connected to the vehicle body. This point will be connected to the tire, to the wheel, to the tire, right? So these 2 points to the vehicle body, and this is to the tire, maybe the axle here. The purpose of this design is to allow this C point to move nearly vertical. Yeah. So if this rotate and the C maybe slightly go here, but it's nearly vertical. So the purpose of the suspension can be fulfilled. And the C point will be difficult to move in these longitudinal directions of the vehicle. The other design, it is shown here. It is a robot linkage. It is designed with the same purposes, just to allow the C point move in this vertical direction, but not in this longitudinal directions. The other also shown down here, which is called a Chebyshev linkage and Ivan linkage. Again, it is designed such that the C point only move in the vertical directions. So as a complete suspension system is shown in here. Watt suspensions. This is a Watt suspension. This one is the Watt suspensions, and added with Panhard arm. You already understand this Panhard arm is introduced to prevent the movement in lateral directions, and the Watt suspension will prevent the movement in longitudinal directions and allow only this axle to move in horizontal directions. Okay, so clearly that this bar system only prevent the movement in lateral and longitudinal, right? But it doesn't reduce the vibrations. And the one that reduce the vibration is the leaf spring. So clearly that in order for you to have a fully functional suspension, you need the leaf spring that reduce the vibration. You need the Watt linkage to avoid the movement in the longitudinal direction, and the Panhard arm for the lateral directions, right? And so that is a simple mechanism that we use as a suspension. And vibration is crucial, and many studies address the issue of vibration and how you minimize the vibration. And one quantity of interest I have been discussed earlier is the mesh ratio. That the comfort is higher if the unsprung mass, which is the whole system, the suspension system, is much lower than the body of a vehicle. So to improve the comforts, then we got to introduce higher the mass of the vehicle in comparison to the suspension system, right? Okay, so one thing I like you to do, I don't know whether you can do it, is whether you can write a small piece of program, maybe in Excel or in Python, whatever language you have, and try to sort of develop, try to project the trajectory of C when this theta angle is increased by 1 degree, 2 degree, maybe until 20 degree, and 20 degree down here. Okay, so minus 20 and up to 20. And I wish you to be able to plot the movement of the C point. I expect to see that the C point may go here, right, and go down here. So you can assume A and B to have the same length. You can introduce a couple of centimeter and find a way such that you can plot the movement of the C point. You can assume the location, the difference of the location between the top bar and the lower bar. What we wish to see is to see how this point move with the movement of this A bar and the B bar. All right. Yeah, I think you can solve this problem at home maybe later. Now let's discuss further some design
Sorry, Rosa
criteria
Guruwan. Sorry, can you hear me?
for the suspension system.
Rosa Guruwan. Can you hear me?
Traditionally, when you use the axles and leaf spring, the movement between the left and the right are there's
Hello. Hello, Rosa Guruwan.
okay. Is there any questions?
Hello. Can you hear me?
All right.
Hello.
Yeah, so the movement between the left and the right of the wheel are connected somehow. And what we wish now is to is there any questions? No? Okay. Yeah. So now let's discuss a simple design so that the left and the right are not connected. And if they are not connected, then we allow sort of an independent movement between left and right suspensions. And two design that allow that movement is called A-arm and McPherson suspensions. And they are shown down here. Oh, okay. So yeah, no problem. You take your time. Oh, okay then.
Okay.
Yeah. So I will continue the discussion next week then. Yeah. Is it okay? Okay. Thank you so much. I see you again next week. Thank you.
Yes.